To understand the log laws, it's important to relate them back to the index laws that you already know. Now, this law involves multiplying and adding. Now, when we're adding, because we're adding two logs together, they have to have the same base. And when we do that, we find that we get a log of the multiplication of what the numbers in the log actually were, and we keep the base the same. Now, this looks a little bit funny. We use this both ways. We either use it to tidy up when we have two logs that can be added together to simplify and make one expression, but we also use it to take one expression and break it up. And we can pretty much do that by saying whatever we've taken the log of, if it's a composite number, it will have factors. We can take any two of its factors and split it up like this. Now, the law that, of course, we're relating to is this one. When you multiply exponential or index expressions and the bases are the same, we already know that we need to add the indices. So what's happening here is that these are indices and we're adding them. And we know that when we do that, the bases have to be the same, A, and A. And we also know that it only happens when we multiply together the actual numbers. And in this case, the X and the Y are the numbers, which explains why they get multiplied. Now, two simple proofs. The first one is quite easy to follow and explains just why it works. And then I'm going to give you a second one to help you get your head around it. The first proof says, let's put A to the power of all of that. So that's what we have up here, the log of X plus the log of Y, both to the base A. Now, we already know using this law here that if we have an index expression like this, we can split it up into two parts. And that's what we've done here. We've split it into the two bits. Now, another thing we've already learned is that any number, let's call it X, can be written as a power of any other number, as long as you make any number to the power of a log with the same number as the base. So here we've got an A here and an A here. And that X up there really can be simplified to just say the whole expression equals X. So what that means is that this whole thing here really, we could say, could be simplified as X. And this whole part here can be simplified as Y. So basically we just have X times Y, or XY. We can then use this law again and say, well, if you can rewrite X by saying it's A to the power of a log with a base A of X, then surely you can rewrite XY by saying it's A to the power of a log with base A of XY. Now, what have we done? Well, we've started with this expression, A to the power of all of this, and we've finished with A to the power of that. Now, if these two things are equal, then this part I've underlined here, which is this, must be equal to this part I've underlined here, which is that. Now, another way we can prove that this is true is we can say, let's let this part of the expression equal m, and let's let the other part of the expression equal n. Now, once we've written these both out, we can rearrange them and say a to the power of m equals x, and we can say that a to the power of n equals y. So we have these expressions. All right, how's that helped us? Well, let's start with the left-hand side, which is equal to all of this. And now that we have an expression defining what this part is, we know that this part, we've said that that's m, so we can replace that with an m, happily enough. We've also said that this part here is equal to n, so we can replace that with an n, and we get m plus n. Okay, how does that help? Well, if we look at the right-hand side and write that expression out, we now have an expression for x and for y. So instead of writing x and y here, we can actually sub in what x is here and what y is here. Now we've got a to the power of m times a to the power of n, and we already know what that gives us. It gives us a to the power of m plus n, doesn't it? So that helps me get to this line. We also know that this entire expression here comes out as just m plus n, okay? And that's because of that law that we already know, which says we can rewrite any number like this, just by using something raised to the powers and the logs cancel each other out. So if the left-hand side equals m plus n and the right-hand side equals m plus n, then we've proved that it works out. Now we use this law to simplify log expressions. So for example, if you've got two logs to add together and you can see that the bases are the same, then all you need to do is multiply the numbers 5 and 4 to get 20. So that's quite simple. We also use it to break logs up. Now, why would you want to break logs up? Well, Sometimes once you've broken them up, you can simplify them more easily or combine them with other like terms. So, for example, here we've got an expression that's saying 8 to the power of something is 40. Now that's not a nice round number. It's not one we can do easily. But we can break 40 up into various factors. Now when thinking about what factors you'd like to break it up into, it sort of helps you simplify it. For example, I could break it up into, say, log base 8 of 4 plus log base 8 of 10, because I know that 4 times 10 is 40. But instead of doing that, I'm going to break it up into 8 and 5. And the reason I'm doing that is because I can see that this part's going to simplify quite nicely. 8 to the power of 1 is 8. So I can see that this whole part here is 1. And this part, well, 5 is a prime number, so I can't really break it up anymore. So I know that I've got down to an answer that is as simple as it can go.